So we're going to go through this section on metamorphic rocks. Um, and these are the rocks that start their lives as something else and then become changed or metamorphosized into a new type of rock that can retain a lot of its original characteristics as far as mineral content, but are distinctly different from what they started as, from their parent material. So real quick review of where we've gone, where we've been. We looked at igneous rocks. Of course, igneous rocks are made from cooled magma, either inside the earth or from lava cooling outside of the earth, separated by grain size into intrusive from magma, and then extrusive from lava, and then intermediates like porphyritic. We also looked at sedimentary rocks. Sedimentary rocks are made from the weathered particles or of other rocks or organic material or something that comes out of a solution of water, precipitate. These are rocks that are built of other types of material. And then the last one, the ones that we're going to look at today, are metamorphics. They are made from other rocks that are changed primarily by heat and pressure. So that's the process. Metamorphism is the process where heat, pressure, or even a chemical process can change one type of rock into another. So they are either a sedimentary rock, an igneous rock, or they can even be another lower grade metamorphic rock that is subjected to even more heat and pressure to become something new. As you drop down into the earth, a couple of things happen. One, of course, is that the pressure increases. Just like going to the bottom of a pool, you've got the weight of all that water on top of your head. So the further down you go, the more the pressure. You also have heat rising as you go further and further into the crust. So this heat and pressure very deep in the earth can cause a rock to change or metamorph. Think of metamorphosis like metamorphosis of a caterpillar into a butterfly. It starts out as one thing, ends up as something else. It's changed. Metamorphosis. So metamorphic rocks become something new, but they can very often retain a lot of those original characteristics because they're actually made of the same minerals. It's just that those minerals have been realigned and now have formed something new because of that realignment of the mineral grades. There's two ways metamorphosis typically happens, regional and contact metamorphism. We're going to explore a little bit about each type. So the first one let's take a look at is contact metamorphism. Contact metamorphism is pretty small scale. And this typically happens due to heating. So imagine a situation where material from the mantle is allowed to push up into the crust. It starts out as a solid in the mantle because of the pressure, but as it rises, the pressure is reduced, allowing it to become a liquid. So say we have a magma chamber or some other type of intrusion into the crust. The intense heat from that magma can very often change the rock surrounding it into a new type of rock or a metamorphic rock. For example, in this graphic here, you'll see in this picture, you'll actually see a few things. So this dark colored band that you see is an igneous sill. It is magma that pushed in between two layers of rock. In this case, on both sides, above and below, is limestone. The intense heat from that magma caused the limestone to metamorphosize into a new rock called marble. Again, it contains the same minerals, but the minerals have been altered and realigned. You'll also notice, of course, that the igneous material cooled into an igneous rock. The other type is called regional metamorphism, and these are much more large scale and are attributed mainly to intense pressure. These large areas can be many states or even countries. Think of very large pieces of our crust, tectonic plates, that are pushing against or sliding past each other. Along those contact areas, along that plate boundary, you'll often find metamorphic rocks, typically created by that intense pressure, that movement of those rocks over millions of years. You'll look in this graphic here, the A and B. Here we have a mountain building episode where two pieces of crust are pushing against each other. you'll see that there's a wrinkling effect, but that high pressure can create metamorphic rock. So very often if you're driving in the mountains and you see some rock that has some wavy lines in it, that's typically caused by regional metamorphosis. In the B, you also have, these are areas called subduction areas where a piece of crust actually pushes back into the mantle, just kind of pushes it as it's pushing, it goes back into the mantle or subducts. You'll often find metamorphism occurring along that boundary as well. We classify metamorphic rocks into two main types, and it's just based on the alignment of the mineral grains. It is foliated. I always think of foliage like leaves, leafy, and then non-foliated. Foliated metamorphic rocks show banding. So the banding, as you can see in this picture, can be multicolored. Perfect example is a rock called gneiss, and we'll talk more about that in a minute. Or the banding can be the same color, but the material still looks leafy. So I've got a quick little animation to show you. So in this animation, we have a pretty typical igneous rock called diorite, primarily made up of three minerals: amphibole, quartz, and plagioclase feldspar. So as this material is pressurized and heated, contact or regional metamorphism, the mineral grains will realign themselves. Think about like rice in a cup, and they're all kind of scattered. You start shaking the cup, and the minerals, the rice will start to align itself into these nice bands, and that's exactly what happens in case of a metamorphic rock. The minerals align themselves into nice, even bands. Non-foliated rocks are exactly the opposite. They do not show that banding. The mineral grains have been realigned and altered, but they just don't show that typical banding that you see with a foliated rock, and are usually pretty uniform in color. So some examples of foliated metamorphics. The first example here we have is shale, which is a sedimentary rock, but under heat and pressure becomes something called slate. Still retains a lot of shale's properties in terms of foliation. So you'll see in this rock here, this rock example, that it is foliated. If the slate is subjected to even more heat and pressure, it can become a rock called phyllite. That's the second example there. That's a higher grade metamorphic. The picture on the far right here is a very, very common metamorphic rock, a foliated metamorphic rock called gneiss. Gneiss's parent rock material is usually some type of granite or very similar felsic igneous rock. It can have multiple different parents, but the metamorphic rock form is usually just referred to as gneiss. And then the last one down here is a metamorphic rock called schist, again, which is a large category, can have multiple different types of parents. But in this case, this is from the igneous rock basalt. Non-foliated metamorphics, the two best examples I can give you are quartzite, which forms from sandstone, and marble, which forms from limestone. So we're going to look at just a couple of quick progressions of one rock type into a metamorphic rock. On this first one, we have limestone, and you can tell this is fossiliferous limestone because you can see the imprint of the shell there. Under metamorphic heat and pressure, becomes marble. Sandstone, again, sedimentary rock, glued sand sediments, basically. Under metamorphism, becomes the non-foliated form quartzite. Here we have the progression of shale, sedimentary rock, into slate, a lower grade metamorphic. But then as more heat and pressure are applied, we can get to phyllite and then the schist. The schist is the highest grade metamorphic. I think the last one we have is granite to gneiss. Granite, of course, extremely common igneous rock, probably the most common igneous rock. And then under heat and pressure, of course, the mineral grains realign and it becomes a rock called gneiss. And there's tons of jokes about this. I might be nice, but don't take me for granted. Some uses of foliated metamorphic rocks. Because these rocks have undergone heat and pressure, they've been tempered. It's almost like you take iron and you add heat to it very slowly. You can temper it into a much harder material. So like car tools and things like that, the steel has been tempered so that they're tougher. So for foliated metamorphic rocks, the instant use that typically comes to my mind is something that's going to be outside. So landscaping stones, you probably may have or have definitely seen borders, walls, things like that. And you can see the picture example there. And also slate roof shingles, which aren't commonly used here in the States, but I know in a lot of Asian countries, they do use and have slate roof shingles. They're extremely tough, extremely durable, and they break into nice sheets, kind of like minerals that cleave. So because of that banding, a lot of times these foliated metamorphic rocks will break into nice even sheets that can be used for different things. Just as a side note, slate roof shingles are extremely durable. One small problem, they're extremely heavy. So during earthquake episodes, a lot of the damage to the house actually is from the shingles. Non-foliated metamorphic rock can be broken and into nice round edges. And so this makes it, and of course it's still very tough, very durable. This makes it a perfect candidate to use for architecture, things that are going to be outside, because it's able to resist weathering pretty well. So architecture and of course statues. Here's something interesting. In a lot of metamorphic rocks under certain conditions, the mineral crystals can realign themselves in a repeating pattern over and over again till eventually you'll actually see the mineral within the metamorphic rock. These are called porphyroblasts. And the most common example that I can think of is garnet. So if you look at the picture here, this red looking mineral that is exposed, this is actually a mineral called garnet. And they form under that intense heat and pressure. As the metamorphic rock is subjected to all this pressure, the minerals can realign themselves, of course, but in some cases where they're concentrated, you can have these porphyroblasts. It's a really good indicator that the rock is metamorphic if you see these large porphyroblasts sitting inside of a rock. That's it. If you would, please take a moment to just kind of review the vocabulary through this very simple exercise, just matching. It should be pretty straightforward and self-explanatory. The big thing that I want you to understand about metamorphic rocks, is, as in all rocks, is that they provide clues to the past. They tell us based on how they formed, either from magma or lava, from deposition of sediment, or through heat and pressure. We know that something has occurred there. It gives us a clue to what was going on in the past. So metamorphic rocks especially are able to tell us a lot, either by the type of metamorphic rock or the extent to which we find them. Can point to either regional contact metamorphism, but we know that that area was subjected to heat and pressure from being underground. And so if we find them above ground, we know that there's some tectonic force that brought these rocks to the surface. So as in with all rocks, metamorphic rocks are really going to be a clue to what happened. There's some optional reading for you if you are more interested or like to go into more detail and more depth. The first one is CK12 interactive text. It's a very short reading, but it also has a quiz at the end, some practice questions for you that are good for SOL practice. And then, of course, the whole textbook reading on metamorphic rocks is a little bit more detail. All right, so that pretty much concludes what I was going to go into here. The next thing that I want to talk about, and it's very brief, is the rock cycle. So in Schoology, you should have a link for that to copy that into your drive. In the next video, I'm going to just break it down very briefly. We'll kind of go through and fill it in and talk about how rocks, even though they are ancient and they look like they're going to last forever, they don't. And as they will continually and are continually shaped by forces to change them and move them from one type to another. So thank you very much.